Yeah. Hello, everyone. Uh, in the previous lecture, we have discussed certain important results regarding what is known as a sign of a representation. So we were somewhere around theorem 250, and to establish theorem 250, we made the use of lemma 251, which we did not establish, for which we did not provide the proof in the previous lecture. So in this lecture, we will provide its proof. Great. So, yeah, so let's recall what we have been discussing. So, we have been trying to express an element of Sn as as a product of certain transpositions, and for that we have had a running hypothesis that n is at least 2, because otherwise we do not have any transposition, right? Transposition has to be a 2 cycle. So, we continue with the same hypothesis, n is at least 2, and then move on to the proof of lemma 251, okay? Which says that if the identity element of Sn can be expressed as a product of transpositions, okay, as a product of R transpositions, then this number R, then this number R has to be an even number. So if the identity element is expressed as a product of certain number of transpositions, then the number has to be an even number, okay. So this is what we are going to prove. The proof is interesting. It relies on some sort of induction, okay. Let's see. So first of all, note that R cannot be 1. Okay, just let me write it down here for easy reference. So you have expressed identity as product of R transposition sigma 1 sigma 2 sigma R. Here R cannot be 1, otherwise identity element would be a transposition, so identity element would be equal to a non-identity element. That's not the case. So now if R is 2, then what? We are done, right? Because we have been asked to show that this implies R is even. So if R is 2, then we are done for sure. So then we could assume that R is at least 3, okay. And we can also assume that this lemma holds for all integer s less than R. That is, if the identity element is expressed as a product of s transpositions, okay, for any sort of transposition that one may have, not specifically the sigma is, okay, or one can have some other transpositions also. If the identity element is expressed as a product of s transpositions, then s has to be even, okay. So that's what I mean by this lemma. In other words, let me express it in words. Let me elaborate it. So you assume that R is at least 3, and for any integer s less than R, by that I mean any positive integer s less than R, if the identity element of Sn is expressed as a product of S transpositions, then the number S has to be even, okay. So now let's move on to what we are supposed to establish based on this hypothesis. So suppose we have expressed the identity element of Sn as product of R transpositions sigma 1 sigma 2 sigma R, okay. Then we are going to apply certain standard quote unquote swapping argument. They are not exactly swapping, but anyway, we'll see. To achieve to express E in a form which is more suitable, okay. So we'll explain. So we suppose the last transposition is of the form a comma b, okay, and then how about the previous one? How about the second last one? The second last one is sigma r minus 1. That could very well be a comma b, okay. We know that sigma r is a comma b, so then you know that sigma r minus 1, there is a transposition, right? So it could be of the form, so it is of the form x comma y. Then it may happen that this xy is same as ab, okay, or exactly one of them is equal to exactly one of them, okay, or all of them are different, okay. So it could be that these two are the same, okay, in some order, okay. If xy is equal to ab, then sigma r minus 1 is ab. If xy is equal to ba, even then this is ab, because a comma b is same as b comma a, okay. Suppose one of them matches with one of them, okay. So suppose one of them is of the form, so note that xy is same as y comma x, okay. So you can swap the order, okay. So suppose one of them, so you can assume that the first one is same as a, so then it will be of the form a comma something else c, or it can, or one of them could be b. Suppose the first one is b, then it is of the form b comma something else c, or both of this xy could be different from what we have here, so it could be of the form c comma d. So we have four choices, one, two, three, and four choices for sigma r minus 1, and of course this is sigma r, a comma b. And now if you compute their product, in the first case you find that this product is E, and in the second case this product can be expressed in this form, okay? uh, okay, or rather in this form. You will see its effect in a moment, why we try to express this product in this form. Okay, the reason is that that helps us, okay, not nothing beyond that can be said. uh, and also if you go through the proof, you may call it tricky, but there is a more conceptual proof, but it appears to be notationally more complicated, so I do not want to get into that. Anyway, so if you have this product, it can be expressed as AB comma BC. You can check that. So this product can be expressed as AC comma BD, and CD comma AB can be expressed as AB comma CD. Okay. Anyway, so in the first case we have expressed it as identity. So sigma r and its previous element, I mean previous transposition, sigma r minus 1, their product is the identity element. Okay. Yeah. So this turns out, sorry. Oops. So this turns out to be the identity element, and in that case, in the specific case, identity element is expressed as sigma 1, sigma 2 till sigma r minus 2. Okay. And now we apply the induction hypothesis to conclude that r is even. By induction hypothesis, it follows that r minus 2 is even, and that is equivalent to saying that r is even. So this follows from the induction hypothesis. Okay, so now let's look at the remaining three cases. In the remaining three cases, let me highlight. So this one, and then this one, and then this one. In the remaining three cases, this product turns out to be a comma b, or a comma whatever, I mean a comma b or a comma c or a comma b. So a comma something times some other transposition, this BC or CD here. So note that these three transpositions, note that this one, and this one, they fix A. So these yellow ones, so these yellow ones fix A. Okay. Oh, and now if you look at this violet ones, you'll see that they do not fix A. Okay, so that is the trick that we have done. So we had that sigma r is equal to AB, and now, okay, of course, in the very specific case where sigma r minus 1 is equal to a comma b, then it turns out to be identity, and by the induction hypothesis we are done. And in the remaining three cases, we have expressed the product of the last two terms, sigma r minus 1 and sigma r, as a product of transpositions. What did I do? Just give me a moment. This should be here. Oops. Yeah. Anyway, the earlier marking was not wrong either. Anyway, so in the remaining three cases, we have expressed this product of the very last two transpositions as a product of, let me call it a violet times yellow, okay? And the yellow one, the last one, it doesn't fix, it fixes A, and the first one does not, so the first one doesn't fix A, okay? And now you can apply the same trick to, so you had that E is equal to sigma 1, sigma 2, sigma 3, all the way till the last one is sigma r, the second last one is sigma r minus 1, that one is sigma r minus 2, and so on. So we have been dealing with these two, the last two transpositions together, and now you can deal with the second last and the third last transposition together, okay, where this one is of the form a comma something, right? So now you apply the same trick, okay. The point is that this A element, okay, the transposition containing, or I mean, okay, let me use the knife term containing A, okay. What I mean is that the transposition that do not fix A, this violet one was towards the end, right? Because sigma var was not fixing A, and now you have made the last one, which is this, okay. You have made the last one you have made sure that you have changed the last one to something, okay, which fixes A, whereas we have made sure that the second last one do not fix A. And now you can apply the same trick to the second last and the third last one, that is to the product of the last two, okay. And then you will see that you'll be, I mean, you will land either in such a situation where again you will be done by the induction hypothesis, or uh, or it will follow that this one, or the, I mean, how to write, maybe this blue one is better, yeah. So this has been changed, such that, I mean, to change to transposition which fixes a, sorry, yeah, which fixes a, and now, okay, if you're not in, if you do not land in the first situation, in that case things are easy by the induction hypothesis, then you can change sigma r minus 1 to something such that some transposition that fixes a, and sigma r minus 1, sorry, r minus 2, it does not fix a. Now you apply changes further, okay, only to sigma r minus 2 and sigma r minus 3 together, okay, then it will turn it to something which fixes a, of course, unless you land into a situation like this. And continuing in this fashion, you can make sure that all the last I mean, how to say, all the permutations here except the first one, okay, they can be changed to something which fixes a, okay, and the first one does not fix a. So you have expressed the identity element as a product of r permutations where the first one does not fix a and the remaining one they do fix a, okay. So their product will not fix a, whereas the identity permutation has to fix a, okay. So you have obtained a contradiction. Great. So we won't land in such situations, okay. We will not continue to land in such situations forever, okay. So r has to be even, I mean, sorry, just give me a moment. uh, yeah, precisely, r has to be even. If r is odd, then we will land into the contradicting scenario. So we have to, I mean, things has to factor to the very first setup, okay. Great. And then yeah, and now if you go to I mean, okay, so now we have already discussed this notion of even permutation and odd permutation that we have already defined, that use this theorem 250 as an input, okay, otherwise it would not have had made any sense, okay. So let's recall, an element of Sn is called an even permutation if it can be expressed as a product of an even number of transpositions, and similarly it is called an odd permutation if it can be expressed as a product of odd permutations. If you focus on the even permutations and look at the set consisting of the even permutations of Sn, then that forms a normal subgroup of Sn. This again follows from a straightforward computation. Let's see. So we start with an even permutation of Sn. Okay. So for example, this identity permutation is even. That can be expressed as 1 2 times 1 2. And now if you take two even permutations, sigma and tau, then tau inverse is definitely an even permutation, and the sigma and time tau inverse, that is also an even permutations. So it follows immediately that the set of even permutations of Sn forms a subgroup of Sn. Okay. Sorry, I think. Yeah, the recording is still ongoing. Okay. Great. So now, okay, so it forms a subgroup, and now we are left to prove that this is a normal subgroup of Sn. Okay, so we take an even permutation phi, okay, and now we try to conjugate it by psi. That is, we look at psi, phi, psi inverse. Okay, we need to show that this is even in order to make sure that this is indeed normal. This subgroup that we have just established, this is indeed normal. So we know that this permutation psi can be expressed as product of transpositions. So suppose psi is equal to tau 1 tau 2 tau r, where this tau i's are transpositions. So psi, phi, psi inverse is of this form, right? And then this inverse, I mean, the inverse of this product is the inverse of the individual factors, but in the reverse order, okay? So here you have got r transpositions, and here you have got r transpositions. So altogether from here you end up getting 2r transpositions, and phi being an even permutation, it can be expressed as a product of even permutations, and here altogether you have got total 2r transpositions. So it follows that this is also an even permutation. Okay, so it follows that the set of even permutations of Sn that forms a normal subgroup of Sn. Okay, this normal subgroup is has got a specific name, which is called the alternating group or alternating subgroup of Sn, and it is usually denoted by An. And one can show that the alternating group has got exactly n factorial over too many elements. That is, in other words, this alternating group has order n factorial over 2. Okay, so this is this is standard to, to show, if you have a subset of a, if you have a subset of a set, and if you want to show that it has got cardinality, half, its cardinality is half of the cardinality of the bigger set, then you try to find out a bijection between the smaller set, okay, and its complement. So that is straightforward to do. You take an element sigma from An and send it to 1 to times sigma, okay. And we have just established that a permutation is either even or odd, okay, in the previous lecture based on lemma 251. So this permutation is indeed odd. In other words, it does not lie inside An, so it lies inside this complement of An inside Sn, okay. Then one can show that this is a bijection. To do so, we define a map in the other direction from this complement to An. This sends tau to 1 comma 2 times tau. One can check that both the compositions are identity maps on respective domains, F composed G and G composed F, and that proves that this F is a bijection, so both of them have got the same size, okay. And the union of these two is equal to Sn, which has got n factorial elements, okay. So you know that this n or its complement, both of them has got n factorial over too many elements. Great. Here is an interesting remark, and the next proposition will be follow up in the similar direction. Great. We have been considering the transpositions which are of the form a comma b. So now we'll look at things of bit bigger length, namely 3 cycles. We have been looking at transpositions which are 2 cycles. Now we'll focus on 3 cycles. So note that if you take a 3 cycle ijk in Sn, you know that it can be expressed as ik comma ij. Okay, so this is an even permutation. So a 3 cycle is an even permutation. So more generally, one can show that an m cycle is an even permutation for any odd integer m. Anyway, this is not too difficult to show, and this is something that you have already established in the form of either a lemma or a proposition, where you have expressed, where you have established that a cycle can be expressed as product of transpositions. Okay, this is an immediate corollary of that lemma or proposition. I do not remember what was that. Okay, great. Yeah, okay, so now we move on to the next proposition. So this is about the 3 cycles. So for that, we need to of course assume that n is at least 3, otherwise 3 cycles wouldn't make any sense. Okay, so suppose n is at least 3, then if you look at the 3 cycles lying in Sn, they generate the alternating group. Okay, so let me recall what do you mean by such a generation. It means that the subgroup of Sn that is generated by this, okay, there is a subgroup of Sn generated by the set of 3 cycles that is equal to An. So here you could ask, what does this mean? That a subgroup, sorry, you could ask what does this mean? That subgroup generated by some set. Subgroup generated by some set means the following is the smallest subgroup. Okay, let me just introduce some name. So generated by some set X, is the smallest subgroup containing X. Okay, so here we have got the 3 cycles as our set. So the subgroup of Sn generated by the set of 3 cycles is the smallest subgroup of Sn, okay, that contains this all the 3 cycles or the set of 3 cycles. Okay, we need to show that that is equal to An. So of course, to show that two sets are equal, we first show that A is, two sets A and B are equal. We need to show A is contained inside B and B is contained inside A. Here one of these inclusions is straightforward. So let's focus on the inclusion for which you need to work a bit. Okay, so let us show that An is contained inside any subgroup of An that contains the 3 cycles. Okay, so in that case An will also be contained inside the smallest subgroup containing the set of 3 cycles. Great. So so what is An? So n is the set of all, or the subgroup formed by the even permutation, the subgroup of Sn formed by the even permutation. So let me recall what is an even permutations. Even permutations are those which can be expressed as a product of even number of transpositions. So now let's first take two transpositions and try to compute their product. So if you take two transpositions, so if you take one transposition AB, the other transposition can be of four shapes. It could be A comma B, A comma C, or B comma C, or of the form C comma D, where A, B, C, D are distinct integers. Okay, and in all these cases, you can show that these products can be expressed as, and these products are either, I mean, it can be expressed, I mean, this product is either a three cycle as we have here, or that can be expressed as a product of three cycles. So this can be expressed as a three cycle, okay, or as a product of three cycles. Okay, yeah, great. So you have expressed as we have established, or we have rather observed, that the product of two transpositions is either a three cycle or can be expressed as product of two three cycles. Okay. So now if you have any permutation, that can also be expressed as product of three cycles. Okay, because you can, given an even permutation tau 1 up to tau r, you can how to say, you can combine them, or you can put together in this form tau 1 tau 2 and then tau 3 tau 4 and then tau r minus 1 tau r, and all these permutations are either, I mean, so each of these permutations are either how do you call it, either a three cycle or can be expressed as a product of two three cycles. Okay, and so you know that this permutation sigma can also be expressed as product of three cycles. Okay. So if you look at the alternating group An, it is contained in any subgroup of Sn that contains the set of three cycles. Okay. So for instance, if H is a subgroup of Sn that contains a set of three cycles, then H will also contain sigma. Okay, and that proves that An is contained inside H. Okay, so it follows that An is contained inside any subgroup of Sn that contains a set of three cycles. And the other inclusion is straightforward. Why? Because An contains all the three cycles, right? We have just observed here that if you take a three cycle, then that is even. So An has to contain all the three cycles. So it shows that An is equal to the smallest subgroup of Sn that contains a set of three cycles. Great. So now let's move on to something that we are more familiar with, or you have been familiar for a longer time. So namely these matrices, namely GLNR or GLNC or SLNR and so on. Okay. There are certain interesting properties or subgroups that we have already studied there. So let's see what happens there with some explicit examples. So recall that GLNR is a group consisting of the group formed by the n by n matrices with coefficients in R and having non-zero determinant. So I was a bit surprised. It's a group consisting of n by n invertible matrices with coefficients in R. Okay. And you know that this GLNR has a subgroup, namely SLNR, and that is normal and so on, which is the kernel of this determinant map, etc. So here is an interesting observation that sometimes the complex numbers can be thought of as 2 by 2 real matrices. Okay, so how? So if you take a complex number A plus IB, so think of it in this form. Okay, this 2 by 2 matrix A minus B BA. Okay, if you think of it in this form, then there are such an identification is a nice identification, because the addition and multiplication law of complex numbers behaves well under this identification. Because if you take two complex numbers A plus IB and C plus ID, so if you look at their sum, which is this, on the other hand, if you look at the matrices corresponding to these two complex numbers by this recipe or by this identification, then they are this. Okay, and the matrix that correspond to this complex number is this. This is exactly equal to the sum of the matrices that correspond to these two complex numbers. Okay, and for the multiplication also, one can check that if you take two complex numbers A plus IB and C plus ID, then the matrix that corresponds to the product of these two complex numbers, this matrix is equal to the product of the matrices which correspond to these two complex numbers via this above recipe or via above identification. So this is something nice. Okay, so let me put it in a more mathematical form. So from C to M to R, we have defined this map which sends a plus ib to a minus bba, okay, and we have just observed that it behaves well under addition and multiplication. In other words, that phi of z1 plus z2 is phi of z1 plus phi of z2, and phi of z1 z2 is phi of z1 times phi of z2, okay. Anyway, so this was a warm-up exercise or warm-up yeah, maybe a warm-up exercise, a warm-up example to deal with some of the to get into what we actually want to for today to conclude or before conclusion. So we'll deal with something called orthogonal matrices and special orthogonal matrices and so on, or special orthogonal groups. So if you take a matrix if you take an n by n matrix A with coefficient in R, okay, such a matrix is called orthogonal if its transpose if its transpose is equal to its inverse, that is A transpose is equal to the identity element. And the orthogonal group On consists of such matrices. Okay, it consists of those elements of GL and R such that A transpose is equal to identity. Okay, this set On of GL and R forms a subgroup. Okay, and this is called the orthogonal subgroup or orthogonal. This is called the orthogonal subgroup of GL and R, or it is called the orthogonal group On. Okay, sorry, I'm going to show that this orthogonal going to now indeed show that this On is a subgroup of GL and R. Okay, this is left to you as an exercise. Okay, so try to work on it. This is not too difficult. Okay, you'll get a chance to review the notion of a subgroup. Okay, great. So now if you take an element of On, in other words, if you take an orthogonal matrix, that is a matrix satisfying this condition, A transpose is identity, then there is some condition that gets automatically imposed on the determinant of such a matrix A. So how does it happen? If you look at A transpose, you know that A transpose is same as the identity element, so they both have the same determinant, and the determinant of this is equal to 1. And here you have this, here you have that determinant of A transpose is determinant of A times determinant of A transpose, and this is equal to the square of the determinant of A. So you have just observed that for an orthogonal matrix A, the square of its determinant is equal to 1. So the determinant of an orthogonal matrix is equal to plus minus 1. If you now just focus on those elements of On having determinant 1, then they have a special name that's called special orthogonal group. Okay, in other words, you're taking the intersection of the orthogonal group with the matrices, with the n by n invertible matrices having determinant 1. Okay, so this forms a subgroup of GL and R, or in fact this forms a subgroup of ONR, because this forms a subgroup of ONR and ONR forms a subgroup of, okay, so not because, what I wanted to highlight is that SON forms a subgroup of ON and ON forms a subgroup of GL and R, so this SON also forms a subgroup of GL and R. So here one can show that SON forms a normal subgroup of ON. This is straightforward. Try to apply your knowledge of group homomorphisms. Note that note that SON is precisely the kernel of the determinant map from On to plus minus 1. Okay, and this just being the kernel of a group homomorphism, and determinant map is a group homomorphism, it follows that SON is a normal subgroup of On. Okay, now so now here you have an interesting exercise which is not too difficult at all, or rather which is not difficult at all. One can show that SON has exactly two distinct cosets inside On. Okay, so how could one show that? So let's try to exhibit two cosets. You look at this matrix which has ones along the, you look at this diagonal matrix where the first entry is -1 and the remaining entries are equal to 1. Of course, this is an element of On. You can verify this identity, that A transpose is equal to the identity element, the identity matrix. On the other hand, you note that it has got determinant -1, so it is not an element of SON. So the cosets of SON in On corresponding to these two elements, they are distinct. That is SON and M times SON, where M is this matrix. So these two cosets are distinct because M does not lie inside SON. Now we claim that there are no other cosets of SON in On. So how to establish that? There are several ways. So let's try to follow one approach. So you pick an element of On and try to show that it either lies inside SON or it lies here. Okay. So you pick an element A from On. If A has got determinant 1, then it lies inside SON. Now, if A has got determinant minus 1, then you note that this matrix MA, which is an element of On, this has got determinant equal to 1, okay, because determinant is multiplicative, okay. So this lies inside SON, so it follows that A lies inside M inverse SON, and M inverse is equal to M. So this matrix A of On lies either inside SON or inside MOSN, M times SON. So it follows that these two are precisely all the distinct cosets of SON inside On. So this has got exactly two distinct cosets. Great. Just give me a moment. Yeah. Now one can try to focus on the matrices that has coefficients inside the complex numbers. For that, we can have some analogous subgroups, okay, and we can try to establish results similar to, or we can investigate some such statements, and we will see what happens. So if you take an n by n matrix A with coefficients in the field of complex numbers, in the complex numbers, then you can take its conjugate. That is, you take the conjugate of all the matrices and you take it transpose. So this is called the adjoint of this matrix A. And this is different from the notion of adjoint that you learned while inverting a matrix, okay, while studying the inverse of a matrix, where you replace the entries by the minors of, or probably by the determinant of the minors of up to certain signs. So all that, and that notion of adjoint is different from this notion of adjoint, okay. Anyway, so you look at its bar transpose or its conjugate transpose. What you get is called the adjoint of A, and this is straightforward to see that this adjoint has certain this properties, that the adjoint of the sum is sum of the adjoints, and adjoint of the product is product of the adjoints, but in the reverse order, okay, and so on. So this is something that one can verify, okay, all these four properties, and now one can focus on the matrices satisfying this criterion, that A transpose equal to identity, okay. You can focus on this focus on such matrices A with coefficients inside C that satisfies this condition that A star is identity. Maybe I had just said A transpose is identity. I mean that A star is identity. A times its adjoint is identity. And the subgroup of, in this way, one obtains a subgroup of GL and R. This is denoted by UN, and this is called a unitary group, okay, or unitary subgroup of GL and C. And here one can check that is it if you take a unitary matrix, okay, if you take a unitary matrix, then then the absolute value of its determinant, its square, will be equal to 1. In other words, the determinant of a unitary matrix is a complex number of absolute value 1. Now you can focus on the unitary matrices with determinant equal to 1, and this is denoted by SUN, and this is called the special unitary group, okay. And here are a few things that one can check, that ON is a subgroup of UN and SON is a subgroup of SUN, and for instance that UN intersection GL and R is ON, and all that, okay. And earlier we have seen that SON has exactly two distinct cosets inside ON, okay, and we may expect some such thing here, but it doesn't work. It turns out that SUN, the special unitary group, has got infinitely many distinct cosets inside UN. Roughly speaking, it happens roughly speaking for the following reason, that there are several complex numbers with absolute value 1, okay. Earlier we had only two real numbers with absolute value 1, okay. And now in this context we can have several, of course one has several complex numbers that has got absolute value 1, and that that influences all the cosets, or the number of cosets of SUN inside UN. This is again straightforward to do. Earlier we had considered the matrix having minus 1 and 1s along the diagonal. Now we'll consider the matrix having Z and 1s along the diagonal, where Z is a complex number of absolute value 1, okay. And here one can check that if you look at these two matrices, matrices of this form corresponding to two distinct complex numbers of absolute value 1, okay, to distinct complex numbers z1, z2 of absolute value 1, then this matrix mz1 inverse and then m times mz2, this does not lie inside SUN, so these two cosets are distinct, okay. Yeah, so for any two distinct complex numbers z1, z2 of absolute value 1, you end up I mean these two, I mean their corresponding cosets are distinct, okay. So all these cosets this mz sun, as z varies over the set of complex numbers of absolute value 1, they provide you distinct cosets of sun inside un, and that shows that sun has got infinitely many distinct cosets inside un. Okay, so we conclude here.